Okay, now today we are going to have a look at engineering material, effect of processing on the structure of the material. How does the structure of the material is linked to the processing of the material? What do you mean by the processing of the material? We have different processes: um, casting, forging, rolling, machining, and heat treatment. All these processes affect differently on the grain structure. Now, what is a grain structure? On the microstructure, what is a microstructure? I will explain of the component. Now, when we talk about casting, what actually happened with casting? When you this is a cooling curve for the casting. When you have the molten metal, you pour the molten metal into the cast. So imagine you have a molten metal, you actually pour the molten metal into the cast, uh, into a mold. When you do that one, the metal is higher than its melting point. We do not just melt the metal at its melting point, we increase the temperature as well. So when it touches the mold, the heat transfer will take place and it suddenly doesn't convert into solid. We need some fluidity. After the molten metal is poured into a mold, first thing actually happen is a cooling of the liquid take place. The cooling of the liquid take place at point A. The freezing begins. Now you know when the freezing begin, until all the liquid is converted into solid, the temperature will remain constant, just like the ice melts at 0 degrees centigrade. So 0 degree the temperature, if it's melting, the temperature will remain zero until all the ice has been converted into liquid. Yeah, so similar thing happens. Now, how fast the cooling is, how quick the cooling, it affects the shape, the size, the uniformity of the chemical composition of, and also the grain boundaries and the grain structure and so on. After the freezing end, everything is frozen. It's still hot frozen metal. Yeah, um, solid metal, but still very hot. Then it still actually cools down. The temperature still comes down. Yep. Now, before that one, from this point to here, this was the cooling of the liquid was taking place. From point A to B, from point A to B, this is actually a liquid conversion into solid. Not all the liquid has been converted into solid. When you reach point B, all liquid disappear and we only got a solid. Then from B onward, it's a solid that's being cooled. Now, how do we find what factors affect these cooling rates? The factors that affect these cooling rate is the shape, the size, the geometry of the mold. It also depends on the temperature of the molten metal. It also depends on the surface area of the casting. If the surface area is big, the cooling rate is much faster. Now, the next is solidification time. In the early stage of solidification, if I got, let's say, a mold, I pour the something in the mold. Now in the early stage, what will happen is there will be a solid skin form, because if that's the mold, the metal get in touch with that mold, the rate of heat transfer at this boundary will be a lot as compared to the rate of heat transfer in the middle. Okay, so mold walls are cold, the skin will form. The greater the volume, the slower the cooling rate. If I pour 10 liters of a molten metal, or I put 1 liter of molten metal, for 10 liter, the cooling rate is going to be slower. 1 liter, cooling rate is going to be faster. Now, the greater the surface area, the faster the cooling. Then we got the Chovorinov rule, uh, which is Ts equals C bracket volume over surface area to the power n. C is the constant, Ts is the time, uh, and the n is actually the index it takes. So this actually gives you the cooling rate. Now, what actually happen is we have different cooling rates for different surfaces. There is a different cooling rate between air and metal. There's a different cooling rate between a metal and metal. There's a different cooling rate between liquid and solid. So the all cooling rate are going to be different. Here you can actually see, if imagine this is the melting point. This line is the melting point of the solid. Imagine this is the mold, yeah, and this side it just gives you the distance from the mold, yeah. As you move away from the mold, what actually happen is the temperature gradient increase. What does that mean? The middle of the mold is going to be a lot hotter as compared to the outside layer of the mold, because if imagine a ball, and in the ball you just put like let's say is a hot molten liquid, and which try to solidify. The solidification happens at the boundary because of the air and the mold and the other thing. The rate of cooling is a lot faster, but in the center the rate of cooling is going to be not as fast as in the as at the boundaries. Then there is a thing called dendritic solidification. What is dendritic solidification? Dendritic solidification is when metal is casted, it doesn't solidify uniformly. It forms, this is a mold wall, yeah. It forms the dendrite. Initially, the metal will become solid next to the mold wall, and then it will form dendrites. Dendrites looks exactly like that in casting, and they try to solidify and they try to grow in different dimensions, yeah, yeah, in actually x and y axis and that side as well. And then they actually grow and they actually convert all the liquid that's in the middle here into solid. Now, first dendrite grows from a solid. This will lead to a casting that is not homogeneous. What does it mean by not homogeneous? Because what will actually happen is the molten metal initially, let's imagine it's not 100% pure molten metal. Imagine it's a mixture of two metals. It's a mixture of, let's say, iron and carbon steel. So if you have the whole casting and you just cut the cross section area of the casting, the composition, and if you are able to find the composition of carbon here and the composition of carbon in the middle will be different. They will have different composition, which mean the mechanical properties at the surface will be different. The mechanical properties at the core in the middle, they will have different mechanical properties. Sorry, a bit small, but I will just read that one to you guys. Okay, let me find out. Now, there is a term called segregation. What does the term segregation mean? Segregation mean if I got a casting and let's say it's trying to solidify, and this is the wall of that one, and the solidification is in this direction towards the center. What will actually happen is they will have different composition. That's supposed to be circle, exact circles, which I cannot do. Yeah. So the composition here, metal composition will be different than the composition in the other two eccentric circles. Why is that so? Now the question is, this is a metallurgical rule which says a pure metal has always higher melting point than its other composition, its alloy composition. For example, iron has a melting point of 1400, let's say. Aluminium has a melting point of 660, let's say. If I add, I got 100% pure iron and in that one I add, let's say, 1% aluminium, it's very obvious that now whatever the composition is, melting point will decrease. Yeah, makes sense. But think other way around. I have a pure aluminium, 100% pure aluminium, and which has a melting point of 660 degree. And let's say I got iron, which is a melting point of 1400. If I add iron, 4%, 3% of iron in aluminium, something that has a high melting point, the in logically the melting point should increase now because I have added something of a high composition. Yeah, it's still a little bit, 2%. I'm not adding more than 50%, but 2% it should increase. But according to the rule of metallurgy, the melting point of a pure element is always higher than its alloying composition. So the melting point will decrease as well. We will discuss this in detail when we look at the iron carbon phase diagram. Now, we got two types of segregation. One segregation is known as microsegregation, which occurs over a distance to the size of the compared to the size of the dendrite arm spacing. What is dendrite arm spacing? Go back. Oops, why it's not going back? Then we got the macro segregation. Macro segregation occurs over a similar distance to the size of casting, like quite fairly a large segregation. Now, with micro segregation, there are a lot of processes, complication arises. One of them is shrinkage effect as the casting solidify. It also changes the density of the casting over over the whole casting. We do not want segregation. We want uniform properties. So how we do that one? There's a segregation and there's an anti-segregation process. I will explain that one. It's known as homogenization. I will discuss what homogenization is in detail. Now, microsegregation, we remove that one by a process known as homogenization, which is a process where we heat it at certain temperature where all the elements diffuse together and forms a uniform solution. Macrosegregation affects a larger distance and is difficult to remove in the through this annealing method or heat treatment method, but it can be reduced. It can be reduced by carrying out the mixing during the solidification phase. If I give you example, if you got water, next time when you go home, just take a tap water, do an ice, boil a water, and use that water to make an ice. You will see two different type of ice. One will be cloudy from the tap water, other will be a crystal clear ice. Yeah, you might have seen where you got an ice, a water, you put that in fridge, take it out, as soon as you shake, it converts into ice. Yep, or the ice start to form. It's known as activation energy. We talk about that in detail. So this segregation we usually can be removed by mixing while the solidification happening, electromagnetic stirrers. Sometimes we use ultrasound, which actually breaks the dendrites, the formation of dendrites. Dendrites forms, dendrite breaks, dendrite form, dendrite breaks. So now the dendrites are not in any uniform direction, and it breaks the whole dendrite structure, which actually cause the homogenization, which does not affect or which actually reduces the macro segregation process. Okay.